Happy Saturday, scientists. Let's review. A shocking video in the works for you today, P3, Electricity and Magnetism. If you aren't yet a subscriber but have the potential to be one, then stop resisting. Okay, I promise, I'll stop with the bad jokes. Let's get to the science. In order to produce a static charge, you need to move electrons from one location to another. You do this using friction, and in order to have them not move back, you also need to have both the substances you're using be an insulator. So usually you have the example of a duster and an acetate or other plastic rod, and at the start that will be neutrally charged, as will the duster. Friction is then going to potentially remove the electrons from the duster and add them on to your plastic rod. The duster will then become lightly positive, the plastic rod will become lightly negative, and that opposite attraction allows the two things to be, for example, held together or to experience a force. This is the principle that's applied, for example, in an electrostatic duster. However, most of our electrical applications come under the concept of current electricity. In current electricity, what you're dealing with is you're dealing with the flow of electrons, and usually this is per second. The current will be measured in amps. Usually what you'll be asked to do is to calculate a charge flow. In order to calculate charge flow, you'll use the equation Q is equal to I times T. In this equation, Q is the charge flow, and the unit for that is the coulomb. I is the intensity of current, so we generally just say the current, and that is measured in amps, and T is the time, and that is measured in seconds. The next aspect to a circuit is the various different circuit symbols that we have in order to draw and picture these circuits much more simply than having to explain to people of different languages what they are. The first symbol is that of a cell, and the shorter, larger side of the cell is negative, the other side of that cell is positive. If you combine multiple cells together, then you get a battery. We also need to know about the instrumentation we have. You'll have, for example, an ammeter to measure the current. You'd also have a voltmeter in order to measure the potential difference. Notice that when I'm drawing these symbols, I'm always including the lines coming out of them that represent the wires that would connect them to the rest of the circuit. The next symbol you'll need to know is the resistor. This is very commonly confused with the fuse, where there is a line down the center of it, but you will not be having to draw fuses, so you should always make sure that you're drawing your resistors without anything in that central box. The next thing to draw is a special type of resistor, and that is the variable resistor, which has an arrow going through it. Variable resistors are able to change their resistance depending on the settings or on other circumstances. There are some resistors that are sensitive to temperature, and those resistors are known as thermistors, and they have this symbol here indicate that temperature variability. There are resistors that are sensitive to light, and those will have two arrows indicating rays of light coming in, and these are known as LDRs, or light dependent resistors. The next symbols that you'll need to deal with are the lamp and the motor. Circuits can be divided into two categories, series and parallel. In a series circuit, there is only one loop, or one path for current to follow. In a parallel circuit, there are multiple branches, or multiple ways that current can get around the circuit. If we take the example of a simple circuit that contains two lamps and a cell, in series it would look like that, and in parallel you would find that each lamp would have its own branch. Important when you're drawing a circuit to draw the connections completed. There are some disadvantages and advantages to both, but one of the main things is that in a series circuit, if one of the lamps stops working and this breaks the current flow, then the entire circuit stops working. Whereas in a parallel circuit, if this lamp stops working, this one is still able to continue. Let's add some instrumentation to our circuits in order to be able to measure some things about them. We'll add some voltmeters, and these are always connected to your circuit in parallel with the component that they're measuring. And we'll also add an ammeter. These are always connected in series. What you'd find when you do these measurements is that in a series circuit, the total potential difference given by the cell is equal to the potential differences of the other parts of the circuit added up, and we'll use Vn here to represent any number. In a parallel circuit, each part of the circuit, each branch, receives the same potential difference, so they are all equal. Again, the n here symbolizes any number of branches. In a series circuit, it's the current that is the same throughout the entire circuit. Whereas in parallel, the current will split into the different branches, and the total current would be equal to the currents of each individual branch added together. Finally, the resistance. The more resistors you add in series, the harder it becomes for current to flow through that circuit, and the total increase of resistance will be all of the resistors in the circuit added together. In parallel, the resistance is slightly counterintuitive. Because you're providing a new path for the resistance, the total resistance of the circuit actually goes down with each new resistor that you add, and the formula to achieve this is that the total resistance is 1 over the resistances of each of the individual resistors, also divided by 1. This isn't a formula that you will have to use very often, if at all, but it's very interesting mathematically. We've spoken quite a bit about resistance, but what actually is it? Resistance is the opposition to current. So it is what is stopping, or the force essentially, that is stopping current from flowing through the circuit. It's not actually a force, but this is an easy way of picturing it. And it is measured in ohms. Ohm was a scientist who came up with a law that governed resistance, and that says that the potential difference across a resistor is equal to the current that flows through that resistor multiplied by the resistance. This has allowed us to produce a number of different graphs to study resistance. If your resistor follows Ohm's law, then your graph will have a perfect straight line, and that straight line would be represented by the formula V equals I times R. And this is on a graph of current as a function of the potential difference. You can see here that no matter the potential difference on that resistor, the current and potential difference have a steady relationship. However, this is not always the case, and there are some circuits where, depending on the potential difference, you will have more this type of relationship. An example of this is a filament lamp, but there are also some specialist applications, for example in a diode, which only allows current to flow in one direction. That's the direction shown by the arrow. There are also, of course, light-emitting diodes, or LEDs. These are the same diode symbol, then they show the arrow, the light. When you're dealing with a diode, it only allows current to flow in one direction. So you'll find that in one direction the resistance is infinite, while in the other the resistance is 0. The next type of resistance graph is for a special type of resistor called the light-dependent resistor that we've already discussed. In that case, as the light level increases, you'll find that the resistance tends to decrease, though there are resistors that are made the other way around. And it's the same case with thermistors. Most are made so that as the temperature increases, the resistance of the thermistor decreases. The next topic to discuss is the concept of power, and there are a few key equations here. But power is a measure of how much energy a device is able to transfer. The energy that a device is able to transfer, measured in joules, is equal to the power of that device multiplied by the time that the device was transferring that energy. In order to calculate the power, however, you will often use the formula that power is equal to the potential difference multiplied by the intensity of current. Remember that V in our equations always stands for potential difference, or in old naming, voltage, and that I is the intensity of current. If you substitute Ohm's law for potential difference, then you'll find that power is also equal to the current squared multiplied by the resistance. The next topic in this section is magnetism, and we'll begin by discussing permanent magnets. Often you'll find these in a lab setting with labeled sides north and south, and sometimes even color-coded, red on the north side and blue on the south side. But what's important about these is the area around them. The area around them is known as the magnetic field, and the stronger the magnetic field, the closer together you'll draw your magnetic field lines. As you get further away from the magnet, those lines are further and further apart. So you can see that there's a strong magnetic field at each of the poles of the magnet and close to the sides of the magnet. But that's not the only thing that's important about a magnetic field. Magnetic fields also have a direction. They go from north towards south. And so therefore your magnetic field needs to have the arrows on it to indicate the direction of the magnetic field. But not all magnets are permanent magnets. Many materials have small sections in them, each section with its own individual magnetic field pointing in various different directions, and so overall that is not magnetic, but each of these little magnetic domains is. If you take the magnetic field from your bar magnet, you can force all of the magnetic domains into alignment. And then your material becomes an induced magnet, because now all of the magnetic fields here are pointing in the direction that you've forced them in, and so they're no longer cancelling each other out. So your induced magnet will then hold that magnetic field for a while depending on its material properties. Some hold it for longer than others. But there is something very interesting about magnets for electrical concern. A scientist by the name of Hans Christian Ørsted was studying what happened as his electrical currents came near to a plotting compass. And he found that when the current, and we're talking conventional current here, was flowing in one direction, he would get a magnetic field in a particular direction. And if the current were reversed, the magnetic field that was around that wire would be reversed. And he came up with what is known as the right-hand rule in order to determine the direction of the magnetic field. So if you picture your right hand with your thumb extended in the direction of the current, and then the fingers of your hand are curling around, and you'll have to excuse my hand drawing here. The fingers of your hand are curling around in order to grab the wire with the current flowing in that direction. The way that your fingers are curling around the wire is the direction of the magnetic field. The closer it is to the wire, the stronger it is, and the further apart you get, the further apart your magnetic fields are. And then you draw in your arrows to indicate the direction of the magnetic field curling around the wire. However, most of the time, as you can tell, we don't really want to draw hands and wires. So instead, we use a cross and a dot to symbolize current direction, and then we draw the magnetic field around those. This is based on the concept of throwing a dart. If you've thrown the dart, then the current is going away from you. So in this case, our thumb would be pointing into the page, and then when we draw our magnetic field around this wire, with the current pointing into the page, we'd find that our fingers are going to curl up over the top of the wire, and that's the direction of that magnetic field. In the second instance, the dart is being thrown towards you, therefore your thumb is coming out of the page, and so the magnetic field will be going in the opposite direction. However, that's not the only interesting thing with magnetic fields. What you can also do with them is you can find a force on them. This is mainly a focus for the higher syllabus, but it's fascinating anyway, so even if you're on the foundation, take a listen. If you take a permanent magnet with its north and south poles, or two permanent magnets with their opposite poles, you'll have a magnetic field between those poles with the direction north to south. Then you can take a wire and put it in the center of those two magnets, and you can determine that the magnetic field around that wire is going in the direction that we've previously done, right? So it's going essentially from right to left across the top, and from left to right across the bottom. What you'll find is at the bottom, both fields are pointing in the same direction, and so the overall field is much stronger. And at the top, where they point in opposite directions, the field becomes weaker. What you'll find then is that the wire will experience a force that pushes it out of the strong area and towards the weak area. So there will be a force in this direction. In order to determine the direction of this force, we use the left-hand rule. In the left-hand rule, your thumb represents the thrust or the force. There's a TH in thumb and a TH in thrust that the wire is going to experience. Your first finger is the magnetic field from north to south, and you need to hold these two fingers at 90 degrees as if you were doing finger guns. You then need to take your second finger and hold it at 90 degrees to the first finger, so it points out to the side, and that represents the current. An interesting application of this scenario is in the concept of a motor. We'll start with our same wire, but then we'll form it into a loop. In this scenario, the current in the wire is going to be flowing around the loop, such as when the wire is on the other side, the current will be flowing away from us. And we can then do the magnetic field around that section of wire, and we'd find the magnetic field there goes in the opposite direction. Therefore, we can determine the force that that wire would experience. In this case, it's going to be the opposite of what we have in the first wire. At the other end of our wires, we'll connect both sides up to a source so that the current is flowing. But instead of having a permanent connection here, we'll use a specialist piece of equipment known as a split ring commutator. What this will allow is for the wire to turn. So, as the wire experiences an upward force on this side, it will move in an upward direction over towards the other side, where gravity would then pull it back into place. Meanwhile, this wire would be forced in the opposite direction. But as they reach the new sides, their connections would reverse. And therefore, the current in that section of wire will reverse, and so it will continue pointing in the same direction as we've drawn in our diagrams, meaning that you will continue to experience a force. And that is essentially what drives your motor. Now you can change the strength of that motor by changing a number of different variables. So the force of our motor is equal to B multiplied by I multiplied by L. Let's take a look at what B, I, and L mean. The F stands for the force on the motor. B is the strength of the magnetic field, and this is measured in Teslas. I continues to be the intensity of current, and L is the length. There is some use to this electricity in the sense that we can make ourselves motors and we can accomplish work with it, but it is important to understand how it all fits together, how these formulas apply, how the current, how the resistance, all of those things change as you change the overall construction of the circuit, so that you can therefore build a circuit to do what you need it to do. I hope that you found this useful. As always, there's a revision sheet down in the description for you, and the answers to that will be up next week. Happy sciencing!